Hello everyone, I'm Bruno Berenguel Baeta, PhD student from the University of Zaragoza, and I'm going to present our article titled FreDSNet, Join Monocular Depth and Semantic Segmentation with Fast Fourier Convolution from Single Panoramas. The problem of indoor 3D understanding is a hot topic in the robotic and computer vision research. In the different tasks, we aim to jointly obtain monocular depth estimation and semantic segmentation from single panorama. We propose to use visual sensors that are lightweight and multifunctional. These sensors can be mounted on several devices, aerial vehicles, robots, and cars. Among the different visual sensors, the classical ones are the perspective cameras. More recent ones are the RGBD cameras, which provide depth information on pair with the color from the perspective camera. We can also obtain depth as a stereo system of cameras. However, we lack context awareness of these systems. On the other hand, omnidirectional cameras provide more information of the environment with a single image. However, there is not any depth sensor for these omnidirectional cameras. The stereo problem is difficult to tackle due to self-occlusion of the cameras. In our work, we tackle these challenges of omnidirectional cameras. We propose the first deep neural network that jointly estimates monocular depth estimation and semantic segmentation from single panoramas. We are the first that used fast Fourier convolution on instant understanding problems. We use these convolutions to leverage the wider receptive field and obtain more context information which can only be obtained from panoramic image. We propose an encoder-decoder network with a branch for each task. We also propose a joint training where each task can benefit from each other. The main body of FreDSNet is composed by encoder and decoder blocks. The encoder blocks are formed by a fast Fourier convolutions named Fourier blocks since we use different activation functions. The output of this block is used as skip connection to the decoder. After the Fourier block, we downsample the feature maps and convolve them. This W convolution is a set of convolutions similar to the bottleneck structure of FreDSNet, where we use convolutions with circular padding due to the continuity of the rectangular panoramas in the horizontal axis of the image. The encoder takes as input the multi-resolution output of the FreDSNet layers added with the output of the previous encoder block. The decoder blocks follow a similar structure but in the inverse order. First, we convolve the feature maps, then we upsample them and add the skip connections, which are weighted by a learning parameter. Finally, the feature maps go through the Fourier block and to the next decoder block. From the main body of the architecture, two branches appear for each of the tasks at hand. Semantic segmentation branch takes the last 5 blocks of the feature maps of the decoder and convolve them into an intermediate representation. Then we make a weighted sum of the feature maps and convolve the resulting feature maps into final segmentation map. The depth estimation branch follows the same principle. However, we only use the last 3 blocks of feature maps of the decoder. These are the maps with higher resolution, which will give the most detailed information of the scene. The training of FreDSNet is made for both tasks simultaneously. Since depth and semantic segmentation share common features, each task can benefit from each other. For joining the information, we propose a combination of loss functions from the training loss. For the semantic segmentation task, we use the common cross entropy, and for the depth estimation loss, we use the adaptive reverse Hoover loss, used in previous works for monocular depth estimation. Additionally, we propose other 2 loss functions. Since the output of the depth and semantic segmentation are different in range, we include a function to force the depth branch to increase the depth range of the output. Besides, to combine the information of depth and semantics, we propose an object-oriented loss where we compute the per-class depth maps. The final training loss is a weighted sum of all of the previous losses. We performed two experiments to evaluate the loss functions proposed and the joint training. In the evaluation of the different loss functions, we observe that the overall performance increases slightly when we add one of the new losses, and increases more when we use all of them. Besides, the joint training of the network performs better than each task-specific solution. So we believe that effectively each task benefits from each other, increasing the performance of the method. The comparison with the state-of-the-art method is made with the only other method that provides both semantic segmentation and depth estimation from single panoramas. We evaluate both networks in the same circumstances, providing only color information as input. With this setup, FreDSNet has slightly better performance on depth estimation than HoHoNet, and outperforms HoHoNet by a margin in semantic segmentation. We also present qualitative results and a comparison with the state-of-the-art. Additionally, with the output of FreDSNet, we can generate several 3D representations of the environment from different tasks. Since we provide semantics and depth, we can divide information to provide specific information for different applications, such as the free floor or obstacles in the scene for navigation and guidance, room layout for unmanned aerial vehicles, or the whole 3D scene with semantic information for object interaction and autonomous robots. Conclusion of this presentation, we have presented the first network that jointly provides depth estimation and semantic segmentation from single panoramas. Our work is the first that uses the fast Fourier convolution for indoor 3D scene understanding to substantiate the joint training of depth and semantic segmentation works and can improve the performance of the network since each does benefit from each other. Code of FreDSNet is available in my GitHub repository. Thank you all for your time. If you have any question, please do not hesitate in writing to my email or ask me during the conference.